Thank you for inviting me. This has been on my to-do list for a long time to come here and maybe start more collaboration between our two institutes. And I'm sitting in this table, and Andrew, Dirk, and John all have degrees from right? And these are the only three people I've met other than Kamran, right? So that already tells us that, Mohsen, that already tells us that we should be doing much more. But so today what I want to talk about is somewhat along the lines of what Kiran was talking about, but perhaps looking at the problem a little more generally on how we can use data to comprehensively inform physics models. And there are a lot of students that have helped in this work, and their names may appear throughout the presentation. But I do want to thank the sponsors before starting off. All right. So these days, big data, data-driven modeling is a buzzword. Everyone seems to be talking about it. Many people claim they're doing it. I might be one of those people who claim it too. But before that, I want to break down the different classes of problems that are being addressed, because there is no taxonomy that exists, and there is a need for one. And I also want to use this chart to maybe set the groundwork for what I'm really interested in this talk and what our center is, right? So at the very top, you have what I call as data decomposition or reconstruction methods, where you have a system and you have some data on the system, and you're trying to get more insight into what the data can tell you about the physical characteristics of the system, right? So that's one. And then what I call as class B is perhaps more classical. You have a given system, some data for some time 0 to t, and then you want to make a future state prediction. Then class C, this is probably perhaps what, say, the weather prediction people do. You have a system X, some data D, and some kind of physical model, and you want to see how well you can predict quantities of interest in the future, right? So classic data assimilation would fall here. But what we're interested in here are what I call as class D and class E. I don't want to be classist here. I'm not saying this is more difficult because, right, it all depends on what the system is, right? So class D is something that I call you have some system under some operating conditions or parameters P, and then you have some data for those operating conditions and a model, and then you want to predict some quantities of interest for other operating conditions, right? So that is what I call as class D. But really what we want to be doing in many different physics problems, turbulence modeling is one, material science is one, is to gather data from different systems at different operating conditions, and then try to predict different quantities of interest in different systems that has some similar underlying physics, right? So we want to develop techniques that can help address class D and class E. That's the general goal. And before making a case for physics constrained data-driven modeling, what I want to do is to give you a very, very simple example, perhaps the simplest possible PD example, where I just want to use data only to discover the underlying dynamics of a PDE and then make predictions, right? So again, the spirit of keeping things simple, I'm taking a linear advection diffusion PDE. Everyone, most of us here have solved it in some settings. Some initial conditions, let's say we have periodic solutions, so Fourier series may work. So what I want to do here is to take snapshots of the solution, of the complete state at some points in time, and then use that to discover the underlying dynamics and make future state predictions. I don't know anything about the PDE, right? So the claim is I'm going to do data-driven discovery of the governing equations. And you may see a bunch of papers floating around with this idea. So one of the techniques that I'm going to use is related to dynamic mode decomposition, but it's really regression. There's nothing more fancy. And the way it's done is, again, you assemble a bunch of snapshots, and then you assemble a time-advanced snapshot, and then you solve a regression problem, and you can find the dynamics. And if you actually, we are all in the business of publishing nice-looking results, and if you actually want to show this very impressive result, it is actually really impressive, right? So what is shown on the left is the true solution. I have x on this axis, I have time on this axis, and the solution on this axis. And this is the initial condition. And what I'm using to discover the underlying data-driven or machine learning model is just 4 snapshots. I go from t equal to 0, t equal to delta t, 2 delta t, 3 delta t, and 4 delta t. And that is all the data that I use. And I'm making future state predictions. Okay? So I'm actually nailing the solution to an amazing degree, right? If that is the end of the story, that's actually amazing. So I've discovered the underlying equation, and I'm making future state prediction, and I used very limited data. And I knew nothing about the underlying PDE. So that looks good. But then if we delve a little deeper, and you want to look at the properties of the system, you can ignore this plot on the left. We just go here. And you can see if you plot, say, the eigenvalues of the system that you discovered, you can see that I've also plotted the eigenvalues of the exact system. There's definitely some eigenvalues you're nailing. And as a consequence, you're doing extremely well in predictions, right? But if you observe closely, the initial condition contained sin x, cos 4x, and cos 6x. So the eigenvalues you nailed just correspond to those eigenvalues that was seen by the data-driven process. Anything else, it's not capturing. So if I have an initial condition that contains a 8x or a 2x, I probably will be doing pretty poorly, right? So basically, the goal is, I can show impressive results, but my fancy machine learning model has discovered things that it can only see. It's sort of obvious, right? Like Kieran was also saying, you cannot trust the model to extrapolate. But I wouldn't call this extrapolation in the classical sense, right? So it's not like I lined up all the data sets and I'm interpolating in between, things like that. It is still doing extrapolation because it has discovered the underlying equations, but it's not seen enough of it. So a quick summary of what I showed is, again, these are obvious things, but even if you look at papers written by some of the big experts in the field, some of these points are not emphasized as much as they should be, at least in my opinion. So basically, the goal is, if we rely purely on data, we may end up requiring too much data. Or if you're lucky enough, we can get a magic basis or set of features that can get us the equations. So don't get me wrong. If I inform the machine learning process slightly differently, I can actually discover the underlying discrete numerical scheme, in which case I can actually solve most of these problems. But I call that as finding the magic basis of features. And of course, this is again very common in machine learning, but as physicists, even I was doing overfitting pretty badly until recently, right? So especially if you rely purely on data, there is a very big tendency to overfit, even if you use cross-validation. And again, there is always this issue of what if we don't have enough data, right? So what I'm proposing here is physics-constrained data-augmented models, because these problems never go away if you're purely relying on data. And well, the reason for doing this is fairly straightforward, right? When there is an underlying equation that can be discovered and you have enough data, data-driven technique can actually get them. But in many, many cases, there may not be a beautiful underlying model that's waiting to be discovered. I think Kieran's problem has more hope because your exchange correlation function, correct me if I'm wrong, is only a function of density, right? So at least we know there is something that's sitting there. But many other problems like turbulence modeling, there is no such magic relationship that we can take advantage of, right? And there are many other things. So there's also a lot of domain expertise, intuition, and there are many models that can get us to the ballpark, right? So why don't we ride on the models and then let data finish the job, right? So that's the idea. So, and then we want to use this for class D and class E, where we are trying to be predictive. And again, if you sufficiently inform the model, you've discovered some functional forms that you could potentially use for extrapolation also. OK, so here is the setting. Now, how do we do this data-augmented modeling process? So let's say we have a true process that's governed by some set of equations. We may know these equations. We may not know these equations. But in either case, for many complex problems, we cannot solve these equations, right? So then, because we can't solve these equations, at least for the problems of interest, we tend to coarse grain these models. And in the process of coarse graining, typically the full solution, the true solution doesn't leave the model because it's nonlinear. So typically we end up with this type of approximation where you have a model for parts of the term, right? So the exchange correlation function again is one such model, right? But of course, there is always a model inadequacy term that is left over because this is never quite accurate for many complex problems. So in a nutshell, some of the techniques that we're doing is to inform the model inadequacy using data. And we don't want the model inadequacy term to just be a function of space or time, because that will be too specific to the problem. So we want to develop these model inadequacy terms purely in terms of the variable that is used in the predictive process, right? It's conditional on some data. So I call this functional augmentation. We've also done other work where we do operator augmentation, right? We can actually discover new operators that can augment the model, right? Additional sets of equations. But today I'm just mostly focusing on this embedded functional discrepancy approaches. Again, a very quick intro to turbulence modeling. Of course, one thing that I want to say is whenever anyone talks about data-driven modeling, it cannot be too generic because there's definitely something that the application brings in that is unique, right? So I just want to present some of this work in the context of turbulence models, but the spirit of the presentation is more general. So typically, if you want to model turbulence, this surrogate variable u bar, as I mentioned in the previous slide, you can treat it as an ensemble or time average. And then that leaves these unknown terms. We have to find a model for this term, and it's typically possible to write equations for this unknown term, but you end up with additional unknown terms. And even with all these advances in turbulence modeling over the past 5 decades or so, these models tend to be very inadequate. They contain maybe 1 to 7 transport equations and a large number of adjustable constants. And one of the issues with turbulence modeling is even if you have a very, very nice underlying idea that's very elegant, like you can come up with one, by the time you actually formulate a predictive model for a complex problem, you've added layer upon layer upon layer of approximations that you've lost the elegance, right? So in some sense, even if you start with a lot of rigor, by the time you have a predictive model, you rely on some amount of luck and some arbitrariness. And of course, there are many new models which have greater sophistication, but then you end up with many of these constants and functions that have to be calibrated. And they tend to be calibrated on very limited data, right? At the same time, it's not news that there's been a lot of data that's come online. We can get very, very highly resolved flow field measurements, for instance, on an aircraft wing. We can do very, very high fidelity calculations, of course, on simplified regimes, but it's still available. So how can we use this data, right? So one of the problems is, even though this type of data has been available for the past 15, 20 years, data has not made a big impact on turbulence modeling, at least until the last few years. And I'll go into some of the reasons as to why that is and how we're addressing the problem. But before that, I want to very quickly give you an outline of what I'm going to talk about today. So I'll talk about how we set up the data-driven modeling problem and how we address some of the issues that have haunted us in the past. Maybe very quickly go through the tools, inverse modeling, machine learning, etc. Maybe not too much detail. And then I'll show one demonstration in having a predictive model that we developed and embedded in commercial solvers too. And depending on how much time I have, I'll go into what we're doing in terms of scaling and computer science, etc., right? And some vision. All right, so this is how we set up the problem. I keep this as, treat this as a schematic, right? This is not precisely what we do, but I just, for instance, we solve a Bayesian inverse problem and not something without regularization, things like that, right? So this is schematic, but I'll get into more details later, right? So this is how we've envisioned the approach, right? First, we assemble a large number of data sets. And then we start with a baseline model. And then we add some model discrepancy term. Again, I'm being a little bit vague here because this is not precisely how we do it in the problem, but just think of it as some functions or operators that are embedded inside your baseline model. And then what I do is I solve an inverse problem to ensure that the output of this model can get close to the data. Okay? So that problem is posed in a Bayesian setting, so we can be rigorous. But the main thing that I want to mention is from each of these different inverse problems, I get a spatiotemporal field, okay, if I'm doing functional inversion, right? So the output of this inverse problem is a full spatiotemporal field for a specific problem. And now what I want, so I call this a process of converting data to information, right? So in many classes of problems, we can go directly to data, machine learn the function, and put it into your model, and it may work. But in many other problems, like turbulence modeling, that will not work because your data sees the data sees something very different from what the model has access to, right? So it won't work. So what this process essentially does is it converts data to information. Okay, so now we have a discrepancy that is consistent with the model. Okay, so that's why I use this step and not just go from data to machine learning directly. But this is not enough in the sense that all of these discrepancies are very specific to that problem and that model and that geometry and that grid, right? So I've not gained any new model from this process, but that's where machine learning comes in. So what we're essentially using machine learning is to convert what I call information to knowledge. And what that entails is taking the outputs of these many different inverse problems, which are spatiotemporal fields, and then use machine learning to map it onto feature space or make this discrepancy now to be a function of variables that are available during the predictive step. Okay? So once we do that, we embed that inside the model. So this is, again, fairly simplistic here, but again, this is just to stress the point. But now we have a model that has your traditional piece and some other piece that comes from this inversion and learning process. And again, the goal is class D and class E, where we learn from some systems and then predict in some completely other systems, which has somewhat similar physics. So maybe this is too detailed, but again, I just mentioned earlier that when we first envisioned this process, when we wrote the proposal to NASA about 4 years ago, we had a horrible idea that we would actually go to data and learn from the data and create a machine learned model and then embed it, and it's the end of story. But this inference step over many, many different configurations is what actually made the data and the model consistent with each other, or the information and the model consistent with each other, right? So that's an important thing. And there are many other things that this methodology can help us address. For instance, we may have data that is very different from what you need for the model, right? We may just have pressure measurements at a few points, and we want to convert those pressure measurements into a model term, right? So it's not like that model term is sitting somewhere and then we learn it. We use the inverse problem to connect the discrepancy to the available data, whatever it is, in whatever form it is, as long as it's informative, of course. And then, so the inference process buys us that conversion of sparse data into larger fields. And then we can handle noise and other things if we are in the probabilistic setting. So yeah, very quickly I'll go through, I apologize for this graph. So the earlier block diagram was simpler, but I just want to give you an idea of how this ecosystem looks like, right? So there is a lot going on. There is data, there is experiments and high fidelity simulations, which we may or may not have access to, but we may have some data. And then there's the inference process, and then the machine learning process that generates some knowledge. It gives you a trained model. It may or may not be sufficient enough, so we may design new experiments. And if you're interested in uncertainty propagation, and because we've trained all of this in a probabilistic setting, you can propagate the bounds and you can get predictive bounds on the answer, right? So you're not just getting numbers, you're also getting bounds. So that's the general setup. But there are mainly 4 different pieces: the inference part, the machine learning, this kind of experiments, which I won't talk about today, and I'll show you some predictive results. So inversion. So there are many levels of inversion that we can do, right? One is inverting for parameters, fairly straightforward. And then the next layer is inversion of functions. Basically, the output of your inverse problem is a field. And at a higher level, you can invert for operators. The very first slide, the second slide that I showed on that, discovering the advection diffusion is essentially operator inference. But here I'm doing function inference. How do you set up the function inference? You have some data that's available. Beta is your unknown function that you are trying to infer. You have model output. And then you have your observational covariance and your prior covariance. And this is a very, very large inverse problem because essentially you're trying to invert a field of betas, right? But it is possible to do this with adjoint-based methods. And if we have enough computing power, we can properly sample the posterior. Otherwise, we may assume that there is some kind of linear structure, so we can get both the inverted field and the covariance. And this is an example where we have the mass, momentum, and energy equations in the full Navier-Stokes. And then you have your turbulence model equations. And we introduce discrepancies in the turbulence model equations. And so I just want to show this for emphasis. So this is flow over a bump. Sounds very harmless, but almost every turbulence model out there fails. Okay? So what we're doing here is we're using skin friction measurements on the bump surface, and we're trying to see what the model discrepancy is. So the blue line you see is truth. Just take it from me. It's truth to some appropriate degree. The green line is what most models would predict. And the red line is what the inverse model, the inverse model assimilates information, and that's what it is saying that the likely solution is. And depending on many of the assumptions that you can make during the inverse process in your Bayesian inversion, you can get a spread, but that's a detail. But I also want to emphasize that this is not impressive because, hey, I got some data and then I assimilated the data, right? So that's not impressive, because we always leave out data and then make sure that we're getting the right answers for the right reasons. So even though we are just using data on the surface, we also want to make sure that predictions in the field are also improved. And looking at, say, the Reynolds shear stress or velocities, they also improve, right? So it's getting right answers for the right reasons. Again, there was a very, very quick snapshot on how we do this inference. The output of this inference is essentially a complete field of discrepancies. Then machine learning, again, I don't have to talk to this audience much about it. All I'd say is it collects these different discrepancy fields and builds this machine learning model. It also tells us what the features are. And many different ways of selecting features. The first thing always is to look inside an existing model and use those features. There are other feature subset selection methods that are, I think, very standard that we can use. Don't want to say much more other than the fact that we've tried various different ideas, neural networks, GP regression. We even developed our own flavor of GP regression. We also have tried symbolic regression, but not successful yet. Symbolic regression can actually give you analytical forms that you can see. But that's in theory. We've not succeeded. But the workhorses for us are neural networks and GP regression. And in some cases, multi-scale GPs give us a lot more. I'll maybe skip through this. But I want to demonstrate how this is being used. And I think we are starting to make a dent in how NASA is seeing it and also how industry is seeing it. So I'll give you one successful example. I can't say that we've been successful in all of our efforts. Okay, so here is how I pose the problem. So let's say we want to predict performance of airfoils, right? So think about airfoil as a wind turbine airfoil, and you care about the lift and drag that it generates. So I also don't want to learn from like thousands of airfoils and then predict in thousands of airfoils, because that would be purely, I mean, that would be nice, but that's not what we're trying to do here. So we want to use very limited data from very few airfoils and then predict in other airfoils. For instance, I'm going to use data only from this airfoil at some few angles of attack at one Reynolds number, and I want to predict the flow in all of these different airfoils at different Reynolds numbers, different angles of attack, etc. Right? So it's not extrapolation in the interpolation in the classical sense, but that's how the problem is set up. And again, I'm going to use the Navier-Stokes, the Reynolds average Navier-Stokes, where the unknown is the Reynolds stress term here. And my turbulence model comes from some equation that you don't care about. Okay, so first step, again, I want to emphasize the inference step here because that is key. And I also want to emphasize that you can work with really small data in many problems. Okay, so what I'm showing here is, again, the pressure distribution on the airfoil surface. And what is shown in blue are experimental pressure measurements, which we literally pulled off of a journal paper or a report, right? And if you run your baseline turbulence model, the industry standard, you get this type of prediction in green. So obviously, it's way off. And then I'm doing two different inversions. For one of the inversion steps, I'm using all of the pressure points on the surface. And for the other inversion step, I'm just using the integrated value of pressure or the lift. Okay. So here I'm using 200 data points to invert a full field. And here I'm using one data point to invert a full field. So this is really limited data, only lift. And both of these give me very similar discrepancy fields. There's definitely some variation here, but that doesn't affect anything that's happening on the surface. But what is important is we're using very, very limited information. This is basically the limit of small data, right? So one data point in this for this Reynolds number and angle of attack. I can, see how well that informs my model by looking at not just the pressure, but also if I look at velocity fields, even that is improved. Okay, this is not true for all of the cases, but this class of problems, just lift data is very informative. So we build a model based off of, I think, 25 or 30 different data points, just lift. And then we deploy it in newer airfoils after the machine learning has been embedded in. And this is an airfoil that the data did not see, and this is the Reynolds number and angles of attack that the data did not see. If you look at how lift and drag are predicted, again, these are the experimental measurements. That's the original data, the original model. This is the machine learned model. In some other airfoils, it's actually doing extremely well, even for drag, so that's a good thing. And these are data sets that the model did not see during training, so we're doing proper validation. So again, blue is the data set blue is the experimental measurements, green is the baseline model, right, which is kind of bad. And cyan is if you actually saw the data, but red is the predictive model that's doing a much better job. And again, we are not using pressure, we're just using lift to train the model. And then we go to these checks, right? So the goal for us is to have industrial impact, which means your model needs to be robust. And here we are verifying the situation. So there are many different ways in which we can train our data, many different choices in the inverse problem, many different data sets. So we collected a bunch of machine learning augmented models. And we confirmed that for problems in which the original model is doing well, the machine learning model does nothing. And for problems where the original model, which is in green, is doing poorly, the machine learning models seem to be all improving, right? And there are indicators that can tell us something about the uncertainty. So, but maybe that's for a different day. Now comes something more interesting. So almost all of the work that I showed until now was done in-house for the airfoil case using our own structured, compressible solver. And then we trained the neural network, made it into a module, and then put it inside a commercially available solver, which is unstructured, incompressible, different meshes, right? So we wanted to see if this was actually portable. Is it something that we are just happy here, just publishing a paper, or is it something that has potential for impact? I won't say impact just yet. So again, when we do that, when we upload this in a commercial CFD solver, it's called AccuSolve for those who follow that, you're getting fairly improved results. I wouldn't say as good as before, but it's there, right? So, but this tells us that there is some generality, and there is hope that we can port it on commercial solvers. You don't need to see that. So at least for the turbulence part, the vision is, so now we have what I call a turbulence modeling gateway, where we have some data there. We've not quite gotten to what we really want to do. But the goal is we want to develop this server where we have continuously curated, say, data-augmented models. And users can potentially upload, download, and process data, generate new maps, generate corrections, et cetera, right? So that's the bigger vision. But right now, we just have some of our own neural networks, like the one that I showed in the previous slide, the portable one. And I think NASA is beginning to test it. And so far, things have gone well. But ultimately, we really want this to be a community-driven site where there are many different data sets and ideas that can come in. How much time do I have?
I think a couple more minutes.
Couple more minutes, OK. OK, so maybe I'll just take a minute and say, so most of what I showed so far is smaller problems, and it was specific. But we're also, in our center, we are scaling this up to many different problems. We've actually architected a computer system from, I would say, scratch with IBM's help in terms of having a dual storage. You can have, say, Hadoop and conventional storage. Large training tier for fast machine learning, and there is a testing tier. This is where the work happens during the predictive process, right? So we have very fast GPUs that do specific, say, machine learning evaluations. Not quite as nice as the TPUs, but close enough for us. And then this is supposed to be This is supposed to be used while the HPC solver is running, the flow solver is running. I just want to say something quick. Well, we saw this data, the information to knowledge to prediction process. And there's always, when you talk to people in the field, the real experts, machine learning always tends to be a black box, right? They don't like it. It's something that's sitting inside a box that you don't understand. But I want to say that machine learning is an optional step. You don't need to do that. So the information that's generated by the inference process gives you a target for your analytical model corrections. You already have model corrections. You can actually go after it. But you know what to match instead of doing trial and errors compared to before. And also, there's a few other details, right? So there is no reason for you not to give the machine learning model theory and asymptotics. You can embed invariances. There are many other things you can do, right? It can be more than a black box. There are many other different uses for this. One of the main uses that I found so far is with this technology, you can definitely, you may not have the best model, but you can definitely invalidate a model structure. You can say this is what this model is capable of doing under these assumptions. So, and acknowledge the sponsors, and I leave some topics here for discussion. With that, I'll take questions.